Today we'll be looking at optimizing in economics and science. Just as we have in our past sections in this unit, we've looked at a couple of examples to demonstrate our optimization. So today we'll do the same, looking at two different examples. So example 1, a cylindrical chemical storage tank with a capacity of 1,000 meters cubed is to be constructed in a warehouse that is 12 meters by 15 meters and has a height of 11 meters. The specifications call for the base to be made of sheet steel, which costs $100 per meter squared, the top of sheet steel, which costs $50 per meter squared, and the wall of sheet steel costing $80 per meter squared. In part A, we want to determine whether it is possible for the tank of this capacity to fit in the warehouse. If it is possible, we need to find the restrictions on the radius. So what we're going to do to begin is we're going to give us a visual of this. So let's draw this storage tank. Alright, that's going to be in this warehouse. So we know the dimensions of what the warehouse will be. So we can just draw our warehouse here in purple. And I am no artist, but I try. So there's our warehouse, and we know our warehouse is 15 by 12 by 11, all in meters. So now we can draw our cylinder inside. So we have the cylinder inside of our warehouse. As so. Okay, we don't know what the dimensions will be of the cylinder yet. However, we do know that the capacity of this cylinder chemical storage tank has to be 1,000 meters cubed. So just looking at this diagram here, because we have a side of 12, we know that the radius can't be any bigger than half of 12. So we divide 12 by 2. So we get that the radius can be no bigger than 6 meters. So we look at what our max volume could be. So when we're talking about a cylinder, we know the max volume formula is pi r squared times our height. So if we sub in 6 there for our radius, and our height is 11, we're going to get 1,244.07 meters cubed. Since this value is larger than 1,000 meters cubed, we know then that therefore it is possible. So yes, it is possible. So also, if it is possible, we need to find the restrictions on the radius. So since we know from above that our capacity of the tank is 1,000 meters cubed, we can set 1,000 equal to our pi r squared h. Our height isn't going to change. So we're trying to talk about what the restrictions on the radius would be. So we can sub in for our height there of 11 because that is the height of our warehouse. And what we're going to get is that our radius squared is equal to 1,000 divided by 11 pi. And when we do our calculations here, we're going to get that our radius is approximately 5.38 meters. So therefore, the domain is 5.38, which is less than or equal to your radius, which is less than or equal to 6. So what that's stating is that our radius has to be between these two values. Now, in part B, we want to determine the proportions of the tank that meet the conditions and minimize. So in this case, we have minimized the cost. So what is our goal? So I always like to start off with knowing what we're trying to find. So our goal is to minimize the cost. So we know our cost is going to be equal to the metal for the top plus the metal for the middle plus the metal for the base. So when we're doing this, we need to make sure that we're looking at the top, middle, and base. And why I'm highlighting those is because we have a cost for each of those, and that cost is different for the top, middle, and base. So when we're talking also about our formulas, for the top of a cylinder we know is just a circle. So we have pi r squared times 50, because the reason we multiply it by 50 is because it's $50 per meter squared for the top. Now for the middle middle here is just a cylinder part, so it's 2 pi r h times 80, because the cost for the middle of this metal is $80, plus also pi r squared because we have a circle for the base, times 100, since the metal for the base is 100. As you notice here, we have two values, or like terms, pi r squared, so we can add those values together. So we have 150 pi r squared plus 160 pi r h. Now from before, when we were talking about putting a restriction on our domain, we had 1,000 equal to our pi r squared h. Now this is just a little side note here for you guys. So when we do that in terms of h, the reason I'm doing this is because I want to be able to collect some terms here. So we can have this in terms of h. We only want one unknown variable, so our h would be equal to 1,000 divided by pi r squared. So what we have is 150 pi r squared h plus 160 pi r times our 1,000 divided by pi r squared. Now what we can do is we can go ahead and cancel out a little bit. So our pi's cancel out. We have one r here, we have two, so we're left with one r, so one radius, in our denominator there. So our end here is 150 pi r squared plus 160,000 all over r. So again, we want this in terms of one unknown variable. So in terms of our next step, just like we have been doing in our previous sections of this unit, we now want to take the derivative. So the derivative of our cost in terms of r. So we get 300 pi r minus 160,000 all over r squared. Set it equal to 0. So 0 equals 300 pi r minus 160,000 all over r squared. Now I can move our 160,000 all over r squared to our left side and set that equal to 300 pi r. So now I can cross multiply here and then continue up here, and what we get is 160,000 equals 300 pi r cubed. Then we can divide both sides by 300 pi. So those will cancel out, leaving us with r cubed and 169.795 Now to get rid of that cubed, we take the cubed root of both sides. And when we do that, we get that r will be approximately 5.54 meters. So now we can test these values. So when we look at the cost, so remember when we're testing, you're taking your domain, your endpoints of your domain, and you're taking this found point. So we put in 5.38 and we get that it would be 43,379.5. Put in 5.54. We get that it would be equal to 43,343.9. And put in 6, and we get 43,631.27. So you see here that this is indeed our minimum. So therefore, the dimensions are that our radius is equal to 5.54 meters, and height is equal to 10.4 meters. And that height can just be found by subbing in to our 1,000 equals pi r squared h. And now for our second example. A commuter train carries 2,000 passengers daily from a suburb into a large city. So maybe from Burlington to Toronto. The cost to ride the train is $7 per person. Market research shows that 40 fewer people would ride the train for each 10-cent increase in fare. If the capacity of the train is 2,600 passengers and contracts with the rail employees require that at least 1,600 passengers be carried, what fare should the railway charge to get the largest possible revenue? So anytime we're working with a question that is dealing with revenue, cost, we need to have what x is. So let's start off by saying let x represent number of increases. Now setting up our let statements is something that we have started in grade 10 and should be very familiar with. So in our first part we need to do our setup here. So our first part, we want to talk about the number of passengers and the price. So if we're talking about the number of passengers, it states that if we have 2,000, the price is $7. Now 40 less passengers, so 1,960, the price would be $7.10. If it went down another 40, so 1,920 passengers, the cost would be $7.20. And this continues to get to B, that we can have a formula here of 2,000 minus our 40x. So for the number of increases, we lose 40 passengers. Similarly with our price, it's $7 plus our 10. So now we can look at example 2. A commuter train carries 2,000 passengers daily from a suburb into a large city, so say from Burlington to Toronto. The cost to ride the train is $7 per person. Market research shows that 40 fewer people would ride the train for each 10-cent increase in fare. If the capacity of the train is 2,600 passengers and contracts with the railway employers require at least 1,600 passengers to be carried, what fare would the railway charge to get the largest possible revenue? So this question here, something similar to maybe what we've seen in grade 10, 11, is where we need to set up our let statements first. So to begin, we're going to let x represent the number of increases. So with that, we first step here is to set up. So talking about the number of passengers. So what we notice here is that we have 2,000 passengers to begin with. Alright, and what it's saying here is that we would have 40 fewer people would ride the train if we increase the price. So number of passengers is just going to be 2,000 minus our 40x. Now what about our price? So talking about our price starts at $7, which can be found right here in our question. So we have $7, and what it also tells us is that 40 fewer people would ride the train for each 10-cent increase in fare. So that's going to be 7 plus 0.10x. So now let's look at setting up our domain. So again, this is just following the same steps which we have done from the second part in this unit. So second step up is to start our domain, state our domain. So to state our domain, we need to know the number of people. What is our min and our maximum number of people? So when we're talking about our minimum number of people, we know that at least 1,600 passengers need to be carried. So we set our 2,000 minus 40x equal to 1,600. We can do some calculations here and we get that x is equal to 10. That's just simple algebra, bringing things over left and right side. Now if we're talking about our max, we have 2,000 minus 40x is equal to, in our question here, the capacity of the train is 2,600 passengers. So we set that equal to 2,600. Do some calculations here, and we get that x will be equal to negative 15. So therefore, our domain is from negative 15 to 10 inclusive. Third part, we want to talk about what our revenue is. And our revenue is just going to be the number of passengers times our price. So it's going to be 2,000 minus 40x times our 7 plus 0.10x. Now we can expand, simplify this, so we get r is equal to negative 4x squared minus 80x plus 14,000. Now in step 4, we're going to take the derivative of our revenue in terms of x, which is negative 8x minus 80. Second part in number 4 is to set this equal to 0. So we have 0 is equal to negative 8x minus 80. So we get that 8x is equal to negative 80, divide both sides by 8, so we have that x is equal to negative 10. Now in our fifth part here, we need to go and check, okay, and make sure and solve to see if we have our maximum. So when we're looking at our max and our minimum values, what we always want to do is we want to take our endpoints of our domain. So at negative 15, sub that in to our revenue formula, and what you will get is 14,300. Similarly, if we sub in negative 10, we get 14,400, and when we sub in positive 10, we get 12,800. So you notice here that this value, when we have negative 10, is our max. So what is that negative 10? Well, negative 10 is the number of increases. So should we increase a negative number? It's kind of telling us we shouldn't increase, we should actually decrease. So in our last part here, we want to find what our price is. sub that into our price formula. So we get 7 plus 0.10 times negative 10. So our price should be $6.